Today we're going to talk about Cauchy sequences. Let's recap a few ideas from before. Let F be an ordered field, and let's consider the following map. It'll take a number t in F, and it'll return a point xy that's on the unit circle. The idea is that we can take, by looking here at the lower left-hand box, F as a number line, and we can wrap this number line around so that it's a circle. The whole point here is that plus or minus infinity inside of F really becomes the very top of the circle. In this way, we can think of an element t in Fn as a point on the circle. In particular, if we have 2 points on the circle, namely p sub m and p sub n, they are very close in the sense of Euclidean distance if and only if the difference tm minus tn is very small. Similarly, we can think of infinity, that is plus or minus infinity, as the north pole on the unit circle, namely the point 0, 1. This means that we could take a look at the distance between a point, p sub n, on the circle and the north pole, capital N. In particular, the Euclidean distance between p sub n and capital N is very small if and only if the absolute value of t sub n is large. This means that we have a sequence t sub 0, t sub 1, and t sub 2 will converge if and only if, given any epsilon positive, we can find a delta such that the Euclidean distance between p sub m and p sub n is less than epsilon whenever m and n are greater than delta. We'll say that a sequence does not converge otherwise. Here's a motivating question. The monotone convergence theorem gives a criteria for when a monotone sequence either converges or diverges. But what can we say more generally? To get some intuition here, recall that we looked at the logistic equation. We found that when rho is between 1 and 4, then every term in the sequence is between 0 and 1 whenever the initial term, x0, is between 0 and 1. In particular, this will always define a bounded sequence. In other words, as long as rho is between 1 and 4, we'll think of the function that takes a real number x and returns rho times x times 1 minus x as a map that takes numbers between 0 and 1 and returns numbers between 0 and 1. Using this as motivation, we made the following definition. Consider a sequence A. A subsequence is a subset B that is also a sequence. The celebrated Bozano-Viastras theorem says, let's say that A is a bounded sequence. Then A has a convergent subsequence. This result was first proven by Bernardus Bozano in 1817 and later discovered independently by Carl Viastras in the 1860s. For this reason, we call this the Bozano-Viastras theorem. Here's a specific example based on the logistic equation. Let's say that rho is 3.5. We found the following numbers by iterating to look at the first 40 terms. This actually gives us 4 interesting subsequences. When n is a multiple of 4, we see monotone increasing subsequences, and the same holds when n is 1 more than a multiple of 4. On the other hand, when n is 2 more than a multiple of 4, or 3 more than a multiple of 4, we see decreasing subsequences. This means that our sequence A actually has 4 different convergent subsequences. Using all of this, today let's discuss Cauchy sequences. Here's the idea. Let's say that A is a sequence which converges to a limit L. The idea is that the terms x sub n get closer and closer to L, so in particular, they must get closer to each other. Here's how we can make this rigorous. Say that A is indeed a convergent sequence. Then given a positive epsilon, there exists a delta such that the absolute value, xm minus x sub n, is less than epsilon whenever both m and n are greater than delta. Let's try to prove this. Let's say that A converges to a number L. Then this means, given epsilon prime, we can find a delta such that the distance x sub n minus L is less than epsilon prime whenever capital N is less than delta. To this effect, let's choose epsilon prime to be epsilon over 2 so that we have the following two statements. This means whenever m and n are greater than delta, we can take a look at the difference xm minus xn, use the triangle inequality to break this up into two, and each one of these now we can write in terms of epsilon over 2 and combine back together to see that indeed our absolute value xm minus xn must be less than epsilon. We'll use this to make a definition. We'll say that a sequence A is Cauchy if, given a positive epsilon, there exists a delta such that xm minus xn is less than epsilon whenever m and n are greater than delta. In fact, Cauchy sequences are very nice. Here are two properties. First, every Cauchy sequence is a bounded sequence, and second, every Cauchy sequence is a convergent sequence. Let's explain why. We're going to exhibit a bound m such that the absolute value of each xn is less than or equal to m. To this end, let's fix a positive epsilon 0. You can think of epsilon 0 is equal to 1 since we're going to fix it throughout the rest of this proof. We know that there exists a delta such that xm minus xk is less than epsilon naught whenever m and k are greater than delta. We're going to now fix a k in terms of the floor of this element delta. Remember that the floor is the greatest integer less than or equal to delta. Once we do this, we can use the triangle inequality to see that whenever m is greater than or equal to k, then the absolute value of x sub m will be less than epsilon 0 plus the absolute value of x sub k. Again, remember that k here is fixed. So we see now that the absolute value of x sub m must be less than a specific fixed number for all m greater than or equal to k. In particular, we'll see that our absolute value x sub n is less than or equal to m if we choose m so that it's larger than the first k numbers, absolute value of x0, absolute value of x1, all the way through the absolute value of x sub k minus 1, and if m is greater than this bound we just worked out, this epsilon 0 plus the absolute value of x sub k. This actually shows that our Cauchy sequence, A, is indeed a bounded sequence. Let's show the second statement. Recall that the Bozano-Viastras theorem asserts that because A is a bounded sequence, A must have a convergent subsequence. Let's call it B. If we denote L as the limit of this subsequence, we're going to show that L is also the limit of our Cauchy sequence. To this end, let's fix a positive epsilon, and let's denote epsilon prime as epsilon over 2. We'll make two observations. First, since A is a Cauchy sequence, we can find a delta sub 1 such that the absolute value of x sub n minus x sub capital N is less than epsilon prime whenever n and capital N are greater than delta 1. This is just the definition of being a Cauchy sequence. Second, because B is a convergent sequence itself, we can find some delta sub 2 such that the absolute value of x sub capital N sub k minus L is less than epsilon prime whenever capital N sub k is greater than delta 2. Remember that we're using capital N sub k because these are the indices for our subsequence B. Now let's choose delta to be the larger of delta 1 and delta 2. Whenever n is greater than delta, we have the following. Let's take a look at x sub n minus L. L, remember, it was the limit for the subsequence B. We can use the triangle inequality to write this in terms of the absolute value x sub n minus x sub capital NK and the absolute value x sub capital Nk minus L. Now for the first, we know that this is less than or equal to epsilon over 2 because this is how we define epsilon prime. This was the first of our two observations. For the second, we also know that this absolute value is less than epsilon prime because this was the second of our two observations. But now the sum of these is just epsilon, really showing that our absolute value xn minus L is less than epsilon whenever n is greater than delta. Looking at this proof, we've actually shown that the following two concepts are equivalent. First, A is a Cauchy sequence. Again, what this means is a convergent sequence. Again, what this means is there exists some L such that given epsilon, we can find a delta such that x sub n minus L is less than epsilon whenever n is greater than delta. Second, we have a Cauchy sequence. That is, given a positive epsilon, we can find a delta such that the absolute value x sub m minus x sub n is less than epsilon whenever m and n are greater than delta. Here's the fundamental difference between these two. To show that something is a convergent sequence, you must first already know what the limit L is. On the other hand, to show that something is a Cauchy sequence, you don't need to know what the limit is at all. We know that a limit must exist, that's what the proof says, but you don't need to know it beforehand. Let's say that A is a bounded sequence. We know from the Bozano-Velstros theorem that it must have a convergent subsequence, and so it must converge to some limit L. However, notice that A itself need not be a convergent sequence. Indeed, we've already seen some examples by looking at the logistic equation. But here's the funny thing. If A does converge, then it must converge to the same limit that the subsequence converges to. You could see this from the way the proof worked out earlier. We'll end with some thoughts about the arithmetic of Cauchy sequences. Earlier in this course, we defined the real numbers in terms of Dedekind cuts. Actually, we could define the real numbers using Cauchy sequences. Indeed, first notice that any rational number lowercase q is the limit of a Cauchy sequence. This is because we can define a constant sequence where each x sub n is just this constant number q. Therefore, this is a Cauchy sequence and its limit has to be the constant q. More generally, let's let S be any non-empty subset of the rational numbers that has an upper bound. For example, S could be a Dedekind cut, but it doesn't need to be. Since we know that this has a least upper bound, again, remember that we're kind of embedding things inside of the real numbers, we can define a subsequence as a subset of S as follows. Let's let epsilon sub n be 1/2 raised to the nth power. In this case, by using the properties of the least upper bound, we can find a collection of elements x sub n and s such that x sub n plus epsilon sub n is greater than or equal to L. This actually defines a Cauchy sequence because it is a convergent sequence that tends to L. Conversely, let's say that we have a Cauchy sequence. We've already shown that every Cauchy sequence is bounded, so let's consider the following set. It's the set of elements x and f such that x is less than x sub n for some x sub n in our sequence. The point here is that this S actually defines a Dedekind cut, and its least upper bound is the limit of the Cauchy sequence. Putting all of this together, we really do see that if we're given, say, a Dedekind cut, we can construct a Cauchy sequence, and conversely, given a Cauchy sequence, we can construct a Dedekind cut. For this reason, we may identify the real numbers as a collection of Dedekind cuts S, but we can also identify the real numbers with a collection of Cauchy sequences. In order to compute a specific real number instead of this abstract concept, remember that we can either compute the supremum of a Dedekind cut or we can compute the limit of the Cauchy sequence. Let's make this a little bit more precise. Let's let F denote the collection of Cauchy sequences. Then this defines a complete ordered field. In order to show that something is a complete ordered field, we really have to show that 14 axioms are true. But we're going to leave this for the exercises for the breakout groups. Thanks for watching.